Another type of switch mode power regulator is a buck boost regulator. Buck boost regulator is a combination of buck regulator and boost regulator. Depending upon the duty ratio, either we can obtain an average value of output which is less than source voltage, or we can obtain average output voltage greater than source voltage. That depends upon the value of duty ratio. Duty ratio is equal to turn on time divided by total time period. Depending upon that turn on and turn off of the switch, we can either, depending upon the turn on and turn off time of the switch, we can obtain either buck operation or boost operation. The main application of buck boost converter is in regulated DC power supplies, where a negative polarity output may be desired with respect to the common terminal of the input voltage. The output voltage can be either higher or lower than the input voltage based on the duty ratio. Duty ratio is equal to T on divided by total time period. A buck boost converter can be obtained by cascade connection of the buck converter and boost converter. They has two modes of operation. In mode 1, we are assuming that our switch is in on condition. In mode 2, we are assuming that our switch is in off condition. First one is mode on. Mode 1 operation, that is when switch is on. When switch is on, the input provides energy to the inductor. When switch is on, the diode is in reverse biased condition. Then the sources supply energy to the inductor. Therefore, the voltage across the inductor VL is equal to source voltage Vs. In second mode, we are assuming that our switch is off state. When switch is off state, the energy stored in the inductor is transferred to the output. No energy is supplied by the input during this interval. That is, VL is equal to, during that time, VL is equal to V naught. Voltage across the inductor is equal to V naught, average value of output voltage. Now we have to derive an expression for average output voltage. For that, assuming T on time, during the T on time, the voltage across the inductor is equal to source voltage. Therefore, Vs is equal to L into delta I by T1, where T1 is the turn on time. From this, T1 is equal to delta I into L divided by Vs. Now, consider turn off time. During the turn off time, the voltage across the inductor is equal to average value of output voltage V0, which is equal to Va. Va is the average value of output voltage V0 equal to Va. Va is equal to minus L into delta I by T2. T2 is the turn off time. Okay. From these two expressions, we can obtain an expression for delta I. Delta I is equal to minus Va into T2 divided by T2 divided by, from this expression we can obtain delta I is equal to minus Va into T2 divided by L, and from this we get Va is equal to Vs into K divided by 1 minus K, that is average value of output voltage is equal to source voltage Vs into duty ratio K divided by 1 minus duty ratio. Average value of output voltage is equal to source voltage into K divided by 1 minus K, where K is the duty ratio, which is equal to T on divided by total time period T. Okay, now we have to derive an expression for inductance and capacitance. For that we are assuming continuous conduction. By assuming continuous conduction and limiting the current ripple, the inductor current ripple delta I is equal to 2IL, and capacitor ripple voltage delta Vc is equal to 2Va. We get critical value of inductor as R into 1 minus K divided by 2F, and critical value of capacitance as K divided by 2F into R, where R is the load resistance, K is the duty cycle, F is the switching frequency. From these two equations we can design our buck boost regulator.